Hello, everybody, and welcome to the Neo4j Nodes 2022 Advanced track. Today, we're going to be starting with Nadja Müller and Petra Selmer, who are going to be going over the graph pattern matching. Nadja, go ahead and take it away.
All right. So, welcome also from my side to our session about graph pattern matching. We're going to cover two topics for a bit. So I'm going to present a bit about how we do graph pattern matching in Cypher today. And then Petra will talk about what is coming up for graph pattern matching in Cypher in the future, mainly quantified path patterns, which is allowing you to repeat patterns or sub-patterns when you're matching things. What else is there? Right, so we might be a bit short on time. So if we don't get around to answer questions within the session, we will try to reach out and see, have a look at the comments and reply to you. So first things first, what is graph pattern matching to begin with? Graph pattern matching is the problem of finding and returning graph patterns in a graph. And as you can see in the example above, we have some way to doing this in Cypher already. So we have a match expression with a pattern. In this case, you want to match a person that knows an employee. We think that we're quite good already with patching basic things like this. So as long as you can explicitly define all the labels and the concrete path, I think you can express pretty much everything that you can store in the database. There are, however, more complex patterns that we probably want to match as well. And one of the examples of the more complex patterns that we support is our variable length pattern matching. And here you can see an example of where you would like to repeat an edge. And in this case, you want to match, find a path from person to employee, but we don't quite exactly know how many nodes relationships are in between those, and there might also be intermediate nodes. So what this would match with concretely is that you could have one relationship between those two, or you could have one relationship to an intermediate node, and that follows another relationship to the employee node, and so on. So this goes until you no longer find anything. There are a couple of things that we currently can't really express in Cypher. And one of those are what kind of labels you could have in those intermediate nodes. We can also not really see or express what kind of properties are on these intermediate nodes, or express properties within which are not equality predicates. So that means we can't really express that we want to know all the relationships where we know people since 2010, for example. And also an interesting case that is not possible to express is that you cannot really say that how those properties relate to each other. So you cannot really express that the property X on the yellow node should be equal to the property Z on the green node. And a last example that we can't express is that if you actually want to repeat things that are not consisting of a single relationship type. So in this case, if we would, perhaps you would like to repeat, have a repetition on a nodes relationship and then a likes relationship. And the way we can solve this currently in Neo4j is by using the APOC procedure apoc.path.expand config. So here you can define a relationship filter, which is which has outgoing nodes relationships and then followed by an outgoing likes relationship. So that is like the arrow at the end of the label name or type name, sorry. And you can also define something they call the node end filter, which is also symbolized with this outgoing symbol, which will be the last node that you match should have a label employee, essentially. So this is an example that we've seen before. This is based on the Traversal API in the background. And the Traversal API is a Java API that we have, and actually had even before Cypher was introduced into Neo4j. The way we would like to go, and what we're working on currently, is to introduce quantified path patterns. And this will look like this, essentially. So we have this looks very consistent with what you already have in the language. So we match a person, and then we define a relationship pattern that is going to be repeated. So you can see this with the brackets and the plus sign at the end. And then eventually we'll reach an employee. And yeah, so what we think this will have a couple of advantages to have this in Cypher. Mainly, we hope that you also find that it's more readable than the APOC version. And yeah, because it is actually, the APOC version is based on the Traversal API, we will have better memory tracking in Cypher, and it will also be easier to maintain it. So mainly, if you would actually implement this in the Traversal API directly, it will actually require quite some code to do this, because you cannot use the predefined functionalities of the Traversal API. And you might even have to restart your DBMS to make changes. And with that, I think we are ready to go on to topic on what we've been working on concretely, and that is already in 5.0. So, but first thing, a bit of terminology. So in a match statement, we allow a pattern, and this usually consists of node pattern and relationship patterns. And those itself consist of some kind of name for your for the node that you're matching, and then a label expression defining on what kind of node you want to match. And the same for the relationship patterns. You can then further filter on the patterns you want to return by adding where clauses, so you can have property constraints, etc. So what we introduced in 4.4 was that you can now write where clauses in node patterns. And you can see an example here. So this is mostly syntactic sugar, like the other things that we've actually done so far. And I'd hope it helps you at least to write things a bit more clear, I think. And then we also have a where clause in relationship patterns. So this is the same thing, but here you can also see an example that you can still have the maps for expressing equality predicates when you do graph pattern matching. So here the related equals false. Yeah. So this would already solve some of the problems that we've seen before if you would allow it in var length. We currently do not, unfortunately, I don't know, because we are planning to support these in quantified path patterns later on, which Petra will explain. And the last thing that we did in regards to this is that we allow additional operators in label and type expressions. So this includes being able to express combination of labels with and or, and you can also negate conditions that you write. So yeah, and grouping allows you to do more complex expressions as well. Wildcard is something of a new thing that we didn't have before. So this essentially will match on any node that has some label. So I prepared a short quiz for you, and that is, how do you find nodes without any label? So the way that you would have done this in 4.4 looks like this. So you could use the labels function on a node that you match, and you could kind of use the size function to get 0. But with this new functionality, you can actually use the wildcard, which will match on which would match on a node with some label, and then invert it to get all nodes without any labels. And with that, I'm on my last slide, and I will hand over to Petra.
Thank you, Nadja. So just going into slideshare mode. Right, so as Nadja's actually very well introduced, a few new pattern features. Basically, what this actually sets the stage for is new directions for graph pattern matching. So essentially, all of this work that I'm going to be describing to you now is actually part of the upcoming GQL standard. So this is the graph query language standard that we actually are currently designing in the ISO body. So this is actually the same body that standardizes SQL, for those of you familiar with that. And by and large, it actually contains the same people as well. So that's part of, this is basically part of our journey towards actually eventually supporting all of GQL. Anyway, for the graph pattern matching section, what this actually is all about is adding a great deal of expressivity to the match clause. So everything that essentially follows the match clause. And Nadja already showed you an example earlier on. So essentially, it contains many, many features, but probably the most important and foundational one of all is actually something called a quantified path pattern. And as Nadja's already shown, inline where predicates and label expressions, these are actually prerequisite features that are essentially required in order to make quantified path patterns work. Just to also let you know about timelines, we are currently working on this. So we're actually working in a very much an iterative fashion. And this will actually be released over the next coming number of releases in the 5.x series. So please do keep an eye out for that. And just to let you know, once quantified path patterns have actually made it in and have been released, we shall then also be looking at other graph pattern matching features, such as actually being able to express the shortest path of quantified path patterns, something called alternation of path patterns, and other goodies like that. What I do want to preface all of this with is that these features are definitely for advanced use cases. So it's not the case that essentially users beginning with Cypher will necessarily find this useful or workable at all. These are literally for people who are experienced with Cypher and actually want to be able to express more complicated expressions to match patterns in the graph. Furthermore, also just want to make it very clear that we are not removing any existing graph pattern matching features. So for all of those who love and know the existing pattern matching expressions, they will remain. So this is purely additive. Right, so onto quantified path patterns, which essentially we see as being a great leap forward in terms of the expressivity of variable length path matching. I will actually be introducing quite a number of brand new concepts in the next set of slides, so you may want to just have a cup of coffee ready. So the first notion I want to essentially introduce is a path pattern. So this is something we've already been very used to in Cypher over the past few years, but it's actually something we're formalizing now. And all that this is just a pattern expressing a linear path, right? So it's a sequence of node and relationship patterns, as we can see over here. Now, in order to actually explain the semantics of quantified path patterns, there's actually a lot going on. So in my opinion, I think sometimes query text does tend to obfuscate what's actually going on. So what I'm going to be making use of in the next few slides is this notion of a motif. So essentially using a visual abstraction of the path pattern that it actually stands for. So you can actually see this motif over here consisting of 3 nodes and 2 relationships essentially equates to this path pattern structurally represented over here. And this actually would stand for a path pattern such as the one represented right at the bottom. And actually in all of these path patterns, you can actually see at play all of the constructs Nadja already explained. So we could have things like label expressions, we could have things like inline predicates, we could also have things like inline predicates that actually allow you to express conditions between various elements. By elements, I mean nodes or relationships between various elements in the entire path pattern. So actually, if you look at this node pattern over here, in here we actually have the ability to express a predicate between a property on a C node with a property on this A node over here. So just bear in mind that whenever you see a motif looking like that, essentially what's happening under the hood is it equates to a path pattern like so. Right, so this is actually what the syntax looks like. You already saw an example of it earlier on in this presentation. And to be able to express a quantified path pattern, what this actually looks like is the path pattern itself. So this sequence of nodes and relationships, bounded by round parentheses. And then actually there's a postfix quantifier operation that you put to the right-hand side with an optional minimum and an optional maximum bound. So here's an example. So for example, what this actually represents is a quantified path pattern of a node with one relationship going towards the right, abutted by another node, and that this sequence is repeated 1 or more times. And this is just for your information, just a list of quantifiers that we'll be supporting. So there's nothing actually special in here. It's something that you already are very used to using in the current Cypher variable length path matching syntax. So what's actually going on? What is quantification all about? So first of all, quantification can sometimes be a bit of an overloaded term. So if mentally you think of this as repeating path patterns, you pretty much have got it down to a T. So essentially, quantification is the operation by which a path pattern, such as the following up here, path pattern P, is repeated a number of times in a given range. So we take some path pattern P, that's just a bog standard path pattern, we apply to the lower bound, which is optional, ditto with an upper bound, and then we actually end up with a brand new path pattern Q, which essentially is P repeated between lower bound and upper bound times. And it's very important to take note of these parentheses over here. They delimit the scope of the path pattern, which is to be quantified. So let's actually unpack that a bit more, looking at the mechanics of what's going on behind the hood. So imagine we've got the following quantified path pattern up here. So again, it's our 3 nodes, 2 relationships, repeated at least once and at most twice. Let's start simple. And what we actually have going on here is, what's actually going on? So what we do is we take that path pattern P, and basically we've got two copies of it, essentially 2 iterations, the one on the left and the one on the right. What we then do is actually we apply another operation to it. So this is nothing a user would ever need to write or kind of essentially think about. But what's going on underneath the hood is that these 2 path patterns, these 2 copies of P, are essentially placed side by side. We call this juxtaposition, which essentially is just a fancier term for saying put them next to each other. So what actually happens here is we've got on the left-hand side the first repetition of P corresponding to the lower bound there, and the second repetition of P corresponding to the maximum there. Obviously, if we had something like 1 comma unbounded, you could actually have many, many of these repetitions of P juxtaposed side by side. But let's keep things simple. So what actually happens here is that within each copy of the original path pattern, we underneath the hood subscript every variable with a number denoting which repetition it's in. And this is just basically to namespace all of these variables. So in the first repetition of P, all of these variables are essentially namespace, so we know that they actually correspond to the first repetition of P, and so on. What happens next? Right, so you probably are thinking, hang on, this is weird. What's happening here? So we've got these 2 path patterns, these 2 motifs, but there's something very odd going on here. That does not look like a graph. There's no relationship there. What's going on? And this is exactly what juxtaposition is about. So it's essentially a case where we actually have a node pattern occurring right next to another node pattern. And what happens in this case is, to make quantification work, is that these 2 nodes will essentially get merged into a single node. So it's almost a case of, if you look at this structure over here, hopefully everyone can see my mouse, you squint your eyes a bit and you actually get a new composite node. And I'd like to now draw your attention to the top right of the screen where I actually have this perhaps a strange legend going on here. And all that this is actually saying is that within this example over here, we actually have 3 different types of nodes at play. We have a pink node representing any person-labeled node, a yellow node representing any reviewer-labeled node. Putting those together essentially results in an orange node, which has got to have both a person and a reviewer node on that. So using that principle at play, hopefully it's becoming clearer now what's actually happening. And that is that the last node, node number 3, in that first iteration of P, has got to be exactly the same node in the graph as the first node of the second repetition of P. So essentially what happens is C1 and A2 get merged together to form this kind of new composite node. And then this is actually the resulting motif that comes out of this. So essentially it's those 2 become 1. And actually what's happening here is that when we actually are matching data in the graph, what happens is the same node must be bound to C1 and A2, effectively reducing to a single node pattern, C1 underscore A2. And of course, don't forget that this is not something a user would ever actually be writing. This is just how it, what the mechanics look like. What then happens is, and hopefully it was clear when I went through this legend over here, is that all predicates on C1 and A2 will be combined conjunctively. So remember that this yellow node here had a reviewer label. All pink nodes have a person label. Well, if you're combining predicates conjunctively, it means that the orange nodes now that result have got to have both person and reviewer labels. Right, so let's actually unpack that a bit more. So a reminder again that our motif over here actually stands for this path pattern over here. So much, much longer. So we actually are now quantifying that motif. So Q equals P plus. So what this is actually stating is repeat this motif one or more times. And what's actually happening underneath the hood is this motif gets unrolled infinitely many times, or at least it's bounded in the size of your graph. So all results conforming to the following will be returned for Q. It will be all matches to P1, to one iteration of P, as well as, so that's what this union operator is here for, as well as all results conforming to the path pattern P1 repeated twice, so effectively P1 and P2, so like this longer path over here, unioned with all results conforming to P repeated 3 times, and you get the idea, etc. So this will obviously go through until your entire graph has been traversed. So effectively what's happening is this path pattern here gets effectively repeated and traversed. And all results will be returned conforming to every union of each expansion. So you may be thinking, this is great, but does this mean I can only have a quantified path pattern as my top level? Can I only say match P equals some quantified path pattern? No, definitely not. You can actually, within a path pattern, you can actually add fixed length subpath patterns. Plus, you can also add multiple quantified path patterns as well. But if you actually look at this example, what we have here is a quantified path pattern. It's exactly the ones that we've been looking at, repeated one or more times. But also, right at the front, we've actually got this other path pattern. So you can actually use this device to effectively, iteratively compose ever more complicated path patterns, reflecting what it is that you actually want to express and match in your graph. So just a note as well on, like we saw earlier on with juxtapositioning. So if you recall, when we were actually repeating the path pattern a number of times, the same principle actually applies between any last node of a fixed path pattern with the first node of your quantified path pattern. So this is the only place where syntactically somebody would write what effectively looks like 2 node patterns placed side by side. But the caveat is that one or more of these node patterns needs to be inside a quantified path pattern. And effectively, that is actually required in order to anchor the path pattern. So what's going to go on over here, and in fact, we'll see an example in a short while, that actually makes very clear that whatever it is that Z matches needs to be exactly the same node as that matched by the first iteration of this A label, of this A variable node. So actually, without further ado, let's just walk through an example. So here we've got the self-same query I actually had on the other slide. And what we're going to be matching is effectively the following 2 motifs or paths. So let's just step through it side by side and I'll walk you through it. So first of all, let's start with matching the fixed path pattern, or the fixed subpath pattern rather. So going X, which is some company, some works for edge, going through to some node Z, right? And at this moment in time, Z doesn't have any predicates on it, so it could be any node. But anyway, in this particular graph, this is what is matched. And that effectively corresponds to this part of the motif setup here. Let's move on. Now we come to having to look inside our quantified path pattern. And now we have the first iteration of that path pattern, right, i.e. P1. So a couple of things going on here. Node patterns Z and A are actually juxtaposed here. So remember, this is this merging operation. So what actually happens is, as explained earlier, the same node must be bound to both Z and A, and all predicates combined conjunctively. So effectively, what's actually matched here corresponds to this motif up at the top. So it's a fixed portion plus 1 expansion of the path pattern P. Right, moving on. Can we go on? Yes, we can. And in fact, now something else happens. Now this effectively drops down to this second longer motif here, because now we are in the second expansion of P, i.e. we're looking at P2. And something very interesting happens here. Suddenly, in the previous slide, N5 was just simply the endpoint. Here was just a reviewer, ergo it was yellow. Now, though, it's actually become not only the last node of the first iteration of P, it's also now become the first node of the second iteration of P. So therefore, it's become this merged construct. And because it was a person and reviewer, it actually conforms to that expression. And so therefore it actually suddenly brings in another result. So effectively from N5 through to likes, this new relationship over here, through to N6, and then N9 over there. So effectively that corresponds to the segment here. So we've effectively undertaken another iteration of P. And just to quickly end off with, these would be the solutions returned. There's actually a lot going on here, so don't worry too much if this is looking quite daunting. But I just wanted to effectively show you that what the solutions corresponding to the different motifs look like. So effectively, this is all these solutions correspond to that fixed subpath pattern with one iteration of P. And there's only one solution conforming to the fixed path pattern with two iterations of P. And here you can actually see what's actually going on there. And yeah, and I guess maybe the last thing to just mention is that there'll also be a change. So going just back to the query over here. So just like you can do in variable length path matching today in Cypher. So if you actually assign a relationship variable to a relationship that's actually being quantified, you know how you actually can say R colon like star, and then all of your relationships conforming to that will actually be stored in kind of like a list variable or a list of relationship references. The same thing happens to all of the other elements within your quantified path pattern. So A, D, B, E, and C, all of those will actually can actually be projected in the same way. So here we've got A, D, B, E, and C. They all will be lists of element references. So A will actually contain all the node references that correspond to A, D, etc. And here I'm actually just showing you which iteration the A's and the C's, those are the endpoints again, actually fall into. And hopefully that actually has certainly tantalized everyone, and we look forward to your questions. And I just want to essentially conclude with a summary of what we've actually covered today, and just to underscore the fact that this is coming up in the next few releases, and this is just the beginning. There's actually plenty more to come. And thank you for your attention.